After studying this module, you shall be able to understand the concept of measuring variables. Learn the measurement with 4 levels of measurement. Understand the concept of measuring variable. Learn measuring with 4 levels of measurement. Understand the concept of central tendency. Understand the measures of central tendency, mean, median and mode. Concept of variability. Learn the measures of variability, range, quartile, variance and standard deviation, and understand the numerical calculations and properties of these measures of variability. This module takes into consideration the strategies used to describe and organize data. Descriptive statistics helps in discovering hidden patterns that are important to your data. Understanding these hidden patterns in any data is known as exploratory data analysis. Over the past few years, many new descriptive tools have been developed. These tools help in determining the summary which is appropriate for a set of data. In this module, we will discuss and learn about these descriptive tools only. Scales of measurement. Scales of measurement or levels of measurement refers to the relationship among the values assigned to variables in a data. Scales of measurement are basically rules that explain the properties of numbers that are assigned to observations while measurement. Numbers have different importance in different situations. For example, two people who are aged 20 and 40 years respectively may indicate that one of them is twice the age of the other. But if we consider the world ranking of cricket teams, we cannot say that team which is number 1 is twice as good as the team number 2. In 1946, Harvard psychologist S.S. Stevens developed 4 types of scales of measurement to help distinguish the significance of numbers in different situations. Before a dependent variable can be analyzed statistically, it must be measured or classified in some manner. There are 4 major ways to measure variables. These measurement scales are called nominal, ordinal, interval and ratio. These levels indicate the type of arithmetic that is appropriate for the data, such as ordering, taking differences or taking ratio. Scales of measurement are characterized by 3 properties: ordering, differentiability and ratios. Ordering is if a large number indicates a greater value than a smaller number. Differentiability, if adding, subtracting 2 numbers represent a meaningful value. Ratio, if dividing or taking the ratio of 2 numbers represent some meaningful value. The nominal scale. Nominal scales are used when a number is assigned to represent something or someone. This level of measurement applies to data that consists of names, labels or categories. There are no implied criteria by which the data can be ordered from smallest to largest. For example, a person's name. The only requirement of a nominal scale are the categories of these variables must be mutually exclusive, that is, the variables cannot fall in more than one category, and they are mutually exhaustive. There must be enough categories for all the variables to be included. For example, one can either be an American or a non-American, not both at the same time. Examples of nominal variables include a person's race, gender, nationality, sexual orientation, hair and eye color, season of birth, marital status, or other demographic or personal information. Nominal scales often reflect coded data in behavioral sciences. A researcher may code football as 1 and cricket as 2. They may code different types of clothes as 1, 2, 3 and 4 for casual, formal, ethnic and western respectively. These numbers are used to identify different clothing styles and nothing more. Let us have a look at the example to understand it more. Marital status can be married or single. The gender can be male or female. Ordinal scale. The ordinal level of measurement applies to data that can be arranged in order. However, differences between data values either cannot be determined or are meaningless. Ordinal scales have all the properties of a nominal scale, that is, the categories must be mutually exclusive and exhaustive. But in addition, the attributes are ranked in order of magnitude. Hence, this type of scale is used for ranking, rating or grading. A popular example is corporate ranking. The person of a CEO rank is greater than the general manager, whose position is in turn greater than that of an employee. Another example could be ranking of professional tennis players. The person ranked number 1 is considered to be better tennis player than the player ranked 2, and the number 2 is better than the person who is ranked 3. An ordinal scale only indicates which attribute is greater or lesser than the other one. It does not specify how much greater one attribute is from the other one, nor are the distances between the points in an ordinal scale the same. This means that an ordinal scale only conveys order or rank. It does not specify by what magnitude is tennis player number 1 better than tennis player 2. Interval scale. Interval level of measurement applies to the data that can be arranged in order. In addition, differences between data values are meaningful. By definition, interval scales are scales which have no absolute zero and the distances between each value is equal. It has all the properties of an ordinal scale but is better than both nominal and ordinal, as it not only ranks or rates items in an order, it also indicates the distance between any two score points. A very common example of an interval scale is a rating scale, in which the distance between all the points is equal. An interval scale is hence also known as an equal distance scale. For example, if you are asked to rate your satisfaction with the living conditions of your locality on a 5-point rating scale from 1 very dissatisfied to 5 very satisfied, then an interval scale is being used. The limitations of the interval scale is that it does not have an absolute zero. A popular example of a scale having no absolute zero is a Celsius scale or a Fahrenheit scale to measure the temperature. The value of 0 in the Celsius scale is simply an arbitrary one and it does not indicate the absence of temperature or heat. The scale has an application in addition and subtraction to calculate mean, range, variance, standard deviation, correlation and regression. Ratio scale. The ratio level of measurement applies to data that can be arranged in order. In addition, both differences between data values and ratios of data values are meaningful. Data at the ratio level have a true zero. A ratio scale has all the properties of an interval scale and in addition has an absolute zero. An example of this scale is the Kelvin scale, which unlike Celsius and Fahrenheit scales to measure the temperature has an absolute zero, a point at which a substance has no heat. Other common examples of ratio scales include measurement of height, weight, time, etc. Because a true zero is defined, the ratios between scale points become informative. Hence, it is meaningful to say that a 50-meter distance is twice as long as 25-meter distance, and similarly we can make more inferences about other variables also. The ratio scale is ideal in behavioral research because any mathematical function can be performed on the measured values and it can show all mathematical as well as geographical indicators. Comparison of 4 scales is also done to know about their importance and application in the different fields and parts of research. One can have a look at the table and understand the differences, similarities and the points of differences among the scales. Measures of central tendency. Measures of central tendency describe how the data cluster together around a central point. It is the single value that describes the characteristics of the entire data used for statistical analysis. Such kind of value is called the central tendency or an average. Average is a very commonly used term and we use it daily in our lives. We often discuss about what is the average run of the Indian cricketers, that is how much runs they have scored in each game in their career, or the average height of Asians, etc., etc. Average has a subtle different meaning also in statistics. It may be studied as the particular value which is the most representative value for a population or a group. This type of value has a great significance as it portrays the characteristics of a whole population or group. An average represents the whole of the data. It certainly lays between the two extreme points, that is the largest and the smallest. There are 3 main measures of central tendency: the mean, the median and the mode. The mean. Arithmetic mean is a very common and most popular method used in finding average of any distribution. It is denoted by m or x bar and it is the sum of all the observation in a distribution divided by the number of observations. We can have a look at the example and see how numerically the average or the mean can be calculated. The simplest formula for calculation of mean is x bar is equal to sum of x upon n, right, where x bar is the arithmetic mean, sigma x is sum of all the observations and n is the number of observations in the group for which we are calculating the mean. The mean of course can be calculated the way we have our data, that is it can be individual observation, it can be a discrete series or it can be a group data in the form of a frequency distribution. In the coming sections, we can have a look at the different ways to calculate the mean. Example 1 talks about the calculation of mean for the individual observations. The continuous series where the data is grouped, there also the mean can be calculated, and example 2 shows us that. The discrete series, how the mean will be calculated for the discrete series is given in example 3, and similarly properties of mean. Mean is very different from other measures of central tendencies. The mean responses to the definite position of each distribution. Increasing or decreasing the value of a score will always lead to change in sigma x and also changes in the mean of the distribution. The mean can also be called as the balance point of the distribution. There is an algebraic way of stating that mean is the balance point for a distribution because sigma x minus x bar is equal to 0 always. This says that if we express the scores in terms of the amount by which they deviate from their mean, taking into account the negative and positive deviations, then the sum of the positive and negative deviations will always be 0. The mean is sensitive towards the presence of scores at the extreme, whether negative or positive, than compared to median or mode. Arithmetic mean is not always a good measure for taking averages, for example, in an asymmetric distribution. The main advantage of the mean is the fact that it takes all the scores into account. This generally makes it a sensitive measure of central tendency, especially if the scores resemble the normal distribution, which is a bell-shaped distribution in which most scores cluster fairly close to the mean. However, the mean can be very misleading if the distribution differs markedly from the normal and there are one or two extreme scores in a particular direction. As the value of mean is dependent upon each and every value of the distribution, the extreme values may distort the value of the mean. Like we can see in this example that one extreme value has affected the class average so much. The median. The median basically refers to the middle value of the given distribution. It is also important that whenever the median is given as a measure of central tendency, one half of the distribution tends to be smaller than the other half of the distribution, tends to be larger than the median. Median is somehow also known as the positional average method. For instance, expenditure of 5 people is like this. There the median is 6,000 and it lies in the middle or the third term of the distribution. The median in odd distribution can be found by generally looking at the distribution itself. But while calculating the median in an even distribution, there is no such median or the middle term of the distribution. For example, if there are 12 items in a distribution, the median value is 6.5. So we take the average of the 6th and the 7th item and call it as the median. Of course, before the calculation of median, we have to arrange the items in an increasing or decreasing order for individual observation and then calculate the median for the ungrouped data as shown in example 4. The discrete series or the group data, we arrange the data in ascending order and then find the cumulative frequency and apply the formula for the median. As we can see in example 5, the median is found. Similarly, for the continuous series, some steps have to be taken care while finding the median in continuous series, like application of the formula n upon 2 and then to find the exact median by application of the formula which is given as median is equal to L plus n upon 2 minus cumulative frequency upon the frequency into the class width, where L of course is the lower limit of the median class. Cumulative frequency is, CF is the cumulative frequency of the class preceding the median class, F is the frequency of the median class and I is the class interval of the median class. Example 6 illustrates the calculation of median using this formula. Example 7 also gives an illustration of calculation of median when the class intervals are unequal. Properties of median. The median tells us how many items score below or above it is, but it certainly fails to tell us how far away the score is. While finding the central tendency of a skewed or asymmetrical distribution like wages, income, expenditure, etc., median is the most adaptable method than other methods like mean and mode. The median is unaffected by few extreme scores because it focuses only on the scores in the middle of the distribution. The median can be graphically represented, whereas the mean cannot be represented. The median is very unpredictable when the items are small. Main limitation of the median is that it ignores most of the scores and it is often less sensitive than the mean. It is not always representative of all the scores obtained, especially if there are only a few scores. Although the mean is frequently embodied in advanced statistical procedures, the median is not, and it has some use in inferential statistics but much less than the mean. The mode. The mode is the third type of central value of the distribution. It is the value of greatest frequency in the distribution of the score that has the highest frequency. Basically, mode is often said to be that value of the distribution which occurs most frequently. In group data, the mode is taken as the midpoint of the class interval that contains most frequent number of squares. The diagram presents the meaning of mode. The value of the variable where the curve reaches the maximum is the mode. How to calculate the mode for individual observation? We can have a look at example 8. The score that occurs maximum number of times is the mode value. In continuous series, the mode is calculated by the formula mode is equal to L plus F1 minus F0 upon 2F1 minus F0 minus F2 multiplied with I, where L is the lower limit of the modal class, F1 is the frequency of the modal class, F0 is equal to the frequency of class preceding the modal class, and F2 is the frequency of the class succeeding the modal class. If one has to calculate all the three measures of central tendency, then there is a formula adaptable to calculate the modal class, as well as it is shown as a relationship between mean, median and mode. Mode is equal to 3 median minus 2 mean. For the group data in a frequency distribution, of course, mode can be calculated as shown in example 9. Properties of mode. Mode is the most typical measure than mean and the median. As in daily life, we often talk about modal wages, modal shoe size, modal income, etc. The mode is not affected by the extremeness of the scores. Unlike the mean, mode can be very useful in describing qualitative phenomena, and the value of mode can be expressed graphically. There may be more than one mode in a distribution. They are called unimodal, bimodal or multimodal distributions. As there are several formulae to calculate the mode, usually they give different answers. So, of course, mode is not that dependable measure of central tendency. In fact, one may say that it is one of the most unstable method to calculate the measure of central tendency. Measures of variability. In terms of variability, spread and dispersion are synonyms to refer to how spread out the data points are in a distribution. For example, 4, 5, 6 is the data set, then mean is equal to 5. In data set B, 1, 5 and 9, the mean is equal to 5 again. Though finding out a measure of central tendency is important, a measure of variability is equally significant in knowing about a distribution, as we just saw in the example. Measures of variability indicate the degree to which the scores in a distribution are spread out or squeezed together. Though they indicate the dispersion of the entire set of scores, they do not specify the distance between a particular score and the center of the distribution. Variability within a data set can be measured in several ways, which are the range, semi-interquartile range, variance and standard deviation. The range. The range is the most obvious measure of dispersion. The range of a distribution is equal to the difference between the highest and the lowest scores. An example of the use of range to compare spread within data sets is provided. We can see how the scores and their spread is measured by calculating the difference between the highest score and the lowest score. Properties of range are: the range is simple to compute and is useful when you wish to evaluate the whole distribution. It provides a quick but gross description of the spread of scores, and the range is a significant measure of variability when precision is not important. Since the range is based on two outermost values only within a distribution, if one of these is either exceptionally high or low, it will result in a range that is not typical of the variability within the data set. This description of variation may be understated or overstated. The range is more dependent on sampling fluctuations than the other measures. The semi-interquartile range. To reduce the problem of the range being unduly influenced by the extremes of a distribution, the semi-interquartile range is often calculated instead of the range. The semi-interquartile range is a more sophisticated measure that indicates the extent to which the central 50% of the scores within the distribution are dispersed. It is related to the median. The semi-interquartile range is defined as 1/2 the distance from the 25th percentile and the 75th percentile. The 25th percentile is also called the first quartile, which means that it divides the first quarter of the distribution from the rest of the distribution. It is denoted by Q1. The 75th percentile is also called the third quartile because it divides the lowest 3 quarters of the distribution from the rest of the distribution. It is denoted by Q3. By definition, the quartile points are the 3 points that divide the distribution into 4 equal parts. Using this notation, median is the second quartile, the 50th percentile or the Q2. The formula for semi-interquartile range is Q is equal to Q3 minus Q1 upon 2. Let us have a look at the numerical example. We can calculate the semi-interquartile range if we know how to calculate the median. Remember, we did it in the descriptive measures and we know how to calculate the Q3 and Q1 for the ungrouped data. Once we have the Q3 and Q1 values, we apply it to the formula and we get the value of Q, which is the semi-interquartile range. The properties of semi-interquartile range are: the semi-interquartile range is little affected by extreme scores. So it is a better measure of variability for skewed distribution than the range. The semi-interquartile range is more subject to sampling fluctuations in normal distributions than the standard deviation and therefore not often used for data that are approximately normally distributed. The semi-interquartile range is less sensitive to the presence of a few very extreme scores than is the standard deviation. The variance. A much simpler way to define the variance is possible by introducing the concept of deviational scores. A deviation score expresses the location of a score in the distribution by indicating how many score points it differs from the mean of the distribution. A deviation score is denoted by x minus x bar, where x is the score and x bar is the mean, and is computed by subtracting the mean from each raw score of the distribution. In terms of deviation score, the variance is defined as the mean of squares of these deviation scores. The definition formula for the variance of a population is sigma square is equal to sum of x minus mu whole square upon n, where x minus mu is the deviation score, sum of x minus mu square is the sum of square deviation, which is referred to as SS, and it is an important thing or term to remember because we use it very often in higher order statistical work. N is the population sign. The definition formula for variance of a sample is small s x square is equal to sigma x minus x bar whole square upon small n minus 1. Note that we have divided the sample sum of square deviation by n minus 1 in the formula for calculating the variance of a sample. This is preferred by some statisticians because it tends to give an unbiased estimate of the population variance. Cormack and Mental, 1990. However, dividing the sample sum of square by just small n is also not considered wrong. Let us have a look at example for the calculation of variance. The 3 columns are x, x minus x bar and x minus x bar whole square. And on application of the formula for variance, we can arrive at the variance score of 6.8. The computational formula for variance of a population is sigma square is equal to sum of x square minus sum of x whole square upon n and the whole term divided by n again. The computational formula for variance of a sample has the minor change that the denominator is n minus 1 here. Let us have a look at the example and see how the variance is calculated to be 3.5 on application of the formula for the sample. The standard deviation. The variance is used primarily in inferential statistics, although it is a central concept in the design of some measures of association. Though the variance is a very important and widely used measure of variability, especially in inferential statistics, it has a major flaw. Its value is always expressed in squared units, which makes it a less useful tool in descriptive statistics. For purpose of describing the dispersion of a distribution, a closely related statistic called the standard deviation, symbolized as small s or sigma, and which is calculated by taking the square root of the variance, is used. Thus, the standard deviation is the square root of the average of the squared deviations of a set of scores from the mean. That is, the square root of the variance. It is an index of the average deviation of a set of scores from the center of the distribution. Let us have a look at the formula for the calculation of standard deviation. Standard deviation represented by sigma is equal to square root of sum of x minus mu whole square upon n. And for the sample, we know that there is a minor change. Sigma is represented by s and the sample size is subtracted by 1 for the correction that we have discussed above. Computing the standard deviation after knowing the variance is very easy, as it is just the unsquared variance, as we can check out in the formula. To illustrate the concept, let us take an example again and see how the variance is computed in the previous section, and once again we can of course put a small correction of putting a square root here, and we'll arrive at our new statistic called as standard deviation. So the standard deviation formula is just a replica of the variance formula with a minor change that it has a square root over it. An example would illustrate how the standard deviation is calculated, and we find that the standard deviation of the example given here in the table turns out to be 2.16. Properties of standard deviation. The standard deviation is similar to the mean in a way that it responds to the exact location of each score in the distribution. When the skewness of a distribution is bad, standard deviation may not be recommended measure of variation, of course. It has the best sampling stability among all the measures of variability, and it is also not recommended to use when the distribution is open-ended. Summary. Descriptive statistics help in discovering hidden patterns that are important to your data. Scales of measurement or levels of measurement refer to the relationship among the values assigned to variables in a data. 4 scales of measurement have been found: the nominal, ordinal, interval and ratio. The 4 scales have been discussed, and of course along with the measures of central tendency and variance. A measure of central tendency gives you a single score that represents the general magnitude of scores in a distribution. The most common measures for calculating averages or the measure of central tendency are mean, median and mode. Mean is the sum of all the observations in a distribution divided by the number of observations. It is a sensitive measure and a most popular one too. The median basically refers to the middle value of the given distribution and is also known as the positional average method. Median is very unpredictable and used only when the data is skewed. Mode is the third type of central value of the distribution and it is the value of greatest frequency. Mode is equal to 3 median minus 2 mean. The term variability, spread and distribution are synonyms and refer to how spread out a distribution is. So, variability refers to how spread out the data points are in a distribution. The most popular method to study the variability of a distribution are range, semi-interquartile range, variance and standard deviation. The range is simply the highest score minus the lowest score of the distribution. The semi-interquartile range is a more sophisticated measure that indicates the extent to which the central 50% of the scores within the distribution are dispersed. They are more related to the median value. The variance is defined as the mean of the squares of deviation scores and the value of variance is expressed in squared units, which makes it a less useful tool in descriptive statistics. To check this flaw, one can take the square root of the variance and obtain a widely used measure of variability, the standard deviation. The standard deviation indicates how closely the values in a distribution are packed together around the mean. Among the 4 measures of variability, the standard deviation has the best sampling stability among all.